Thank you for the introduction. So as the introduction said, I was in charge of the CGX10 cell isolation development, product managing, and I would like today to introduce you with the CGX10 general system introduction, and then some examples of its use in protocols for generating cell therapy products using multiparametric selection. So first, let me go through the introduction and peek into the instrument benefits, its use and potential applications. And then I will go deeper into some data that we generated with the CCRM, Center for Commercialization of Regenerative Medicine in Canada, going over some examples of use for generating cell therapy products using multi-parameter selection. So the CGX10 cell isolation system is a next generation cell isolation system, leveraging SONY's legacy in the fields of innovation, optics, and automation. The CGX10 cell isolation system is a novel system which enables GMP-ready cell sorting for cell and gene therapy manufacturing. It has a unique and proprietary microfluidic chip and built-in temperature control. It enables fully closed, high-speed, high-purity, multi-parametric fluorescence-based cell sorting for all kinds of cell and gene therapy manufacturing workflows. The specificity or the characteristics of CGX10 can be summarized in these 5 main categories. So first, it's a closed system. Using the proprietary microfluidic chip and the proprietary sorting mechanism, we allow sorting of specific cells, single cell sorting in a closed system. It is GMP ready, both at the instrument level, but also at the single-use kit level, and also on the software level with Part 11 compliance. It is designed with simple operation in mind. It will allow you to operate from the process development mode to the operation mode with the flexible user mode. And also functions like automatic clock detection and recovery would allow you for GMP manufacturing while walking away from the instrument and letting the instrument sort on its own. The touchscreen user interface also facilitates control of the instrument in a GMP cleanroom environment. The sort mechanism itself yields high cell viability. It's very gentle on the cell. And this is also further improved by the use of the active temperature control of the sample and the collection. Both the sample and the collection are controlled in temperature, and the temperature can be set to adjust to any cell type. With the multi-parameter selection features of measurements, it yields reliable data, and the sorting itself is very high speed, it's high purity, and it's gentle compared to similar multi-parameter instruments. You can see here some very simple data summary showing the viability of cells of the CGX after CGX sorting compared to a cuvette sorter. You can see the viability is a few % higher, demonstrating the gentleness of the sorting. So what is included in the CGX10 is, of course, you will get the instrument and the software that is included in the instrument. Then the single-use kit, which consists of the sterile tubing kit, including microfluidic chip. You can see here the design of the microfluidic chip, sample reservoir, salt collection bag, and waste bag. All those come pre-connected, so there is no need for any connection. And aside from these, the standalone sample preparation bag will allow you to transfer the sample from whatever upstream staining process to the inside of the sterile tubing kit. And extenders for sheaths and buffer bags will allow connection to the sterile sheaths and sterile buffer bags used to guide the cells and realize the microfluidic sorting. So the microfluidic chip, which is really where all the magic of the sorting happens is proprietary to this and is included in the sterile tubing kits. And in addition to this, what is really important, of course, is the documentation. So we will provide, SONY provides regulatory and quality support files to enable your clinical and commercial cell and gene therapy manufacturing. So this instrument, the single-use kit, and the software, three main parts of this solution are enabling GMP-ready therapies. They are all manufactured in relevant ISO, under relevant ISO standards, and are provided with the necessary regulatory and quality support file. On the software side, I would just emphasize that it is 21 CFR Part 11, allowing for further integration into electronic systems. So as you are all aware, if we take an example of a CAR-T workflow, there are a number of positions where the CGX10 could be used. We think that it could be used after apheresis and a first debulking of cells, so T-cell isolation, for example, followed by a further sorting to provide the very specific cell subtypes. The other position where it could be used is after gene transfer and somewhere during the T-cell expansion to allow for high purity sorting of the cells that have been correctly gene transduced. An example of use of the CGX10 right after T-cell isolation would be to sort for specific T-cell subtypes using a combination of markers. So you can see on the right here, the differentiation process from naive T-cell to effector T-cells with the stem cell memory, central memory, effector memory. All those are defined by a combination of different markers. The CGX10 would allow you to select for a specific T-cell subtypes, for example, T-stem cell memory, that is in general associated with a higher survival and persistence, and in recent studies in CAR-T, with a higher efficacy of the treatments. With this in mind, we recommend, and this is not limited to those examples, but we recommend the use of CGX10 for cell therapy in CAR-T or TCR-T applications, CAR-NK, CAR-Treg application, and TIL application, as well as gene therapy when cells are used. In summary, the CGX10 cell isolation system is ideal for high-speed isolation of highly pure and viable cells exhibiting different immunological markers such as T cells or NK cells. With its GMP-ready instrument design, single-use kits, and software, the instrument is a first mover in the cell and gene therapy cell isolation space and enables users to navigate the cell and gene therapy manufacturing workflows with confidence. With this, I would like to change a bit gears and go into more of the technical data that has been acquired in collaboration with CCRM. So we have been testing the CGX10 at CCRM for use in cell therapy workflows with two objectives in mind. The first one, and this is the first I will get in more details, is the integration of CGX10 into closed T-cell manufacturing pipelines. We have three examples here. First, a sort of a naive T-cell subset, then a sort of multiple T-cell target populations at fixed ratios, and finally, what we call a bypass or replace of the existing pre-process steps. And in the secondary objective, I will come back a bit later on it, but we will show the utility in iPSC-derived T-cell therapy, derived cell therapy. So first, for the integration of CGX10 into closed T-cell manufacturing pipeline, as I've described earlier, we wanted to take an example where we go to sort a very specific subtype of T cells, one subtype that is associated with higher persistence or higher efficacy in recent study. So as an example, we choose to work with the naive T cell subtype. The therapeutic objective here is to to use less cells for infusion into the patient, and along with this, have a longer efficacy. Also, using less cells might reflect into lower cost of goods for manufacturing and shorter manufacturing time. Here we have been working on naive T cell characterized by CD8 or CD4, CD62L positive expression, and CD45RA positive expression. In general, CCR7 positive expression and CD45RO negative expression can also be used, but we have limited our process to 4 colors. This is a very general overview of the process. So as you can see, we started with fresh apheresis, and using CPACs, the closed system CPACs, we removed the red blood cells by fecal, and then we stained it with beads, CD14 and CD19 beads, to go through a clinimax depletion of the B cells and monocytes. After that, we did a staining using the 4 antibodies mentioned above, CD4, CD8, CD62L, CD45RA. This staining can be done manually or using an instrument like the CPACs. And then we sorted the cells using CGX10. Those sorted cells, when then plated for expansion, activation, and transduction. Here is the result of this experiment. So you can see on the left a representative plot of the CD4 versus CD8 and CD62L versus CD45RA phenotype, pre-sort and post-sort. So as you can see, we have been sorting on the CD4 positive population, CD62L, CD45RA, double positive population. You can see here from the pre-sort to the post-sort, the purity is very clearly improved. And over 3 different, in this case, 2 different donors, you can see that we can bring the population to more than 95% purity after sort. If we look at the sort time and the recovery, you can see on the bottom for the 2 different donors. As an example, we sorted for 4 hours, 200 million cells were input into the system. So that's roughly 50 million cells per hour. And from the target person pre-sort measured on the CGX10, we could recover about 60 to 70% of the cells. The recovered cells viability was also very high, around 99%. So showing that we have no effect, CGX10 sorting has no effect on the viability of cells. Looking further down, we looked at the effect or the difference on the cell expansion after sorting. If you look at the first plot on the left, you can see the unenriched cells fold expansion after 9 days of culture. For untransduced and GFP transduced cells, we see fold expansion below 5, equivalent in both cases. For sorted cells, because also those cells were cultured in naive T cell media favoring naive T cell proliferation, we could see a highly increased fold expansion above 30 times. The next question was whether the CGX10 sorted cells had there was some impact of the sorting on their ability to be transduced. So on the right side, you can see the transduction efficiency after sorting. So if you compare the unenriched cells and the sorted cells, you can see that the transduction efficiency actually is lower on the sorted cells. And I will come back to this point in the next example. But if you combine the fold expansion and the percent of transduction, we still see that the fold expansion of sorted CD4 naive T cells is way higher. It's 3 times higher than the unenriched T cells. So overall, we could demonstrate that the CGX10 sorting did not impact the expansion, had some impact on the transduction, but again, I will come back to this point later. It is not related to CGX10, it's related to the cell population itself. But overall, it yielded more transduced naive T cells than the unenriched population. So with this case study, we could demonstrate that CGX10 used in purity mode is capable of sorting pure population naive T cells with a purity above 95%, both in CD4 case and CD4 naive T cells and CD8 naive T cells. I haven't shown all the data, but we have these N3 and N2 data. Sorted naive T cells at high viability could be transduced and expanded without problem. The next step was to demonstrate another capability of the CGX10, which is the capability to sort multiple target populations at a fixed ratio. So the CGX10 can be programmed to sort cells up to 4 different populations of cells in a predefined ratio. So in that case, we decided to sort CD4 naive T cells, CD4 central memory T cells, CD8 naive T cells, and CD8 central memory T cells, each at a 25% ratio. So this is getting a bit more complicated in the number of parameters we are looking at, but I will try to walk you down step by step. So again, if you look at the pre-sort, post-sort plots, CD4 versus CD8, and within the CD8, CD62 versus CD45RA, then within the CD4, CD62 versus CD5RA, you can see that pre-sort to post-sort on the CD4 versus CD8, we are able to reach roughly 50% of each. And within each of the CD8 and CD4, we again can reach about 50% of each population with a high purity. If we look at the bar plot here, which is a summary, you can see that from pre-sort to post-sort, the population CD8 central memory, CD4 central memory, CD8 naive, and CD4 naive, where before the sort completely randomly distributed, after sort, they get very nicely between 20 and 25%. I think the second donor is even clearer. It's really nicely aligned around the 23-24% mark, showing that the CGX10 can be really configured to sort and output cells at a fixed ratio of multiple target populations. In terms of viability, the results are very similar to the previous case study. The viability is very high, above 98%. And in terms of the fold expansion, again, we could see that there is no impact of the sorting on cell expansion, and rather even more, we can see that the sorted cell expanded better than the cells that were not sorted. Coming back to the point about transduction that I was mentioning a bit earlier, if you remember correctly, the sorted cells in the case 1, in the case study number 1, transduced less than the unsorted cells. Here we can show that the transduction is very much equivalent, showing that the results we had seen earlier was not related to the CGX10 sort, but really related to the cell phenotype and the difference in transduction efficiency of the different cell population between CD4 naive, central memories, etc. So in conclusion of this second objective, so the use of CGX10 purity mode to sort multiple target populations at fixed ratio, we could really demonstrate the ability to sort multiple populations at the fixed ratio of 25%, resulting in cells with high viability, high purity, and that could be transduced and expanded very well. Finally, we wanted to look at the capability of CGX10 to bypass and replace the existing pre-process steps. So I will go into more details in the next slide, but we wanted to replace all the pre-enrichment step and perform T-cell sorting using sorter enrichment mode at an increased speed, but decreased purity, and then do a second run of sorting on purity mode. So going back into the process flow diagram, maybe if you remember, in the previous part, we had, after the CPAC staining, we had a Clinimax step where we debugged the sample and basically depleted the sample from B cells and monocytes. In that case, we worked directly from an apheresis with wash of the cells, RBC lysis, to remove the RBCs and platelets, and directly going to antibody staining and then the CGX10. This is a much more challenging sample. The cell numbers, it's much higher, and the target population, obviously, percentage is much lower. So here again is the same structure. So CD4 versus CD8, CD45RA, and CD62-8 dot plots. You can see here we have three ranges of dot plots. On the far left, you have the pre-sort data, which is the original data. Then we have two post-sort data, one after the enrichment, where we are just sorting to get the maximum of the target cells, and we are not restricting to purity. And then from there, we bring the purity higher with a second sort, and you can see the post-sort purity is very high again. With here, we sorted for the CD8 positive naive T cells. The graph on the right here shows the percent of target cells or purity. So in pre-sort, we started with less than 10%. Actually, on the CGX10, it was 1.3% population. That was enriched to 30 and more in the first step. And this was further enriched into the same purity level we've seen earlier, above 95%. This has been very reproducible across donors. In the table below, I would like to show you some numbers demonstrating the very high speed of this process. So for one donor, that's just an example. In round one, in the enrichment mode, we sorted for 1.7 hours, more than 500 million. So in this enrichment mode, we can sort through more than 300 million cells per hour. This cells target percent was about 1%. And we recovered this, and this enrichment was up to around 30%, as you can see here. In the second round, in the purity mode, we sorted for 1 hour. The speed doesn't need to be that high because we have already enriched, and we recovered 2 million cells in total from the overall process. So enrichment mode resulted in enrichment of target cells as expected, and the second round of sorting then brings the final purity to the same level that we've seen earlier without using any Clinimax step. So we are able to obtain high purity naive T cells using CGX10 and no other processing equipment right from a local pack. I would also like to emphasize that by demonstrating this, we are demonstrating the full range of CGX10 capabilities in terms of sorting speed, purity, and yield. And all this range is totally customizable. So you can decide on a specific purity level that you want to achieve and the speed and yield that you would like to achieve and fit the instrument's operation to your requirements. So on this third objective, we were able to use CGX10 to replace the existing pre-process steps, the Clinimax pre-process step. The sorter was able to enrich and purify a rare population of cells directly from a local pack after staining. Let me go now to the secondary objective, and I will go through some data demonstrating the CGX10 utility in iPSC-derived cell therapy. The importance here is to purify the differentiated cell type prior to formulation. So first, let me go through a bit the idea behind this test study. So in cardiac cell differentiation from iPSC, it is a very promising cell type for cell replacement therapy but the remaining iPSCs are a safety concern, as they may be generating cancers or neoplasma in the future. GMP compatible solutions currently do not exist to purify the differentiated cells and subtypes in the manufacturing of iPSC-derived therapies. So here we took the cardiac cell differentiation, so from iPSC to cardiomyocytes differentiation as an example. The cardiac cells that we decided to work with are differentiated, characterized by VCAM as a surface marker and CTNT, which is an intracellular marker. Of course, we cannot use an intracellular marker to sort for live cells, so we used VCAM as the sorting marker, along with a marker to evaluate and eliminate the remaining non-differentiated iPSC, TRA160. The overall process is a 2 weeks process. So we seeded the iPSCs and started the cardiac differentiation. And around day 6 to 8, we did flow for cardiac and iPSC markers and decided on the best timing for sorting. As we looked into the differentiation of iPSCs into cardiac T cells, we could see from day 0 to day 10 that the expression of VCAM was increasing and the expression of iPSC marker was decreasing. The relevant dot plots with VCAM on the vertical and TRA160 on the horizontal are shown on the top. So because the VCAM expression and the TRA160 expression kind of stabilized between day 8 and 10, we decided that would be the good time for sorting, and especially the TRA160 positive iPSC non-differentiated cells need to be removed for safety considerations, and this is the whole objective of this sorting. So here again, let me go through this slide. So we have the pre-sort and post-sort plots, VCAM versus TRA160. Post-sorting, independently of sorting, we also measured the CTNT marker, which is intracellular, so it could not be used for sorting. But overall, we have been able to show that the purity post-sort is very high, with a percentage of VCAM positive cells averaging around 80%, very well correlated to a positive percentage of CTNT, demonstrating that we actually sorted for the cardiac cells. As for the iPSC marker, it goes down from 10% to less than 1%, demonstrating the capability of CGX10 to actually enrich in the VCAM cardiomyocyte cells, VCAM positive cardiomyocyte cells, while depleting efficiently the non-differentiated iPSC TRA160 positive cells. Finally, the sorting did not impact the viability of the cardiac cells. As you can see here, the viability was around 90% in all sort experiments. As a conclusion, so the CGX10 is a unique closed sorting instrument with customized SUDs, single-use devices, and a GMP-compatible user interface. It has a small footprint and can be easily integrated with other closed upstream and downstream process steps due to its back-to-back and welder-compatible consumable interfaces. It is capable of sorting rare populations with no existing separating strategies using customized markers. The options for purity versus speed, enrichment, we also have modes such as custom purity, where you can really fine-tune the level of purity you would desire. It suits diverse purposes. It can be integrated into a varied cell and gene therapy manufacturing pipelines. And we have demonstrated in this talk the use in CAR-T pipeline, but also in iPSC derived cell therapy pipelines. Of course, when deploying the CGX10 in your pipeline or workflow, the strategy, the marker optimization is required for each target population. The upstream and downstream process need to be co-developed and tailored based on the process. The process time also is dependent on the target person and product scale. And of course, as I mentioned earlier, on the level of purity that you would desire. And then I would like to play a short video resuming the CGX10 capabilities. And I hope the sound plays. If there's anything, just give me. Thank you. I think that's all I had to present to you today. So thank you again for your attention. And I would like to mention that we are grateful to Dr. Shiku from the university who worked with us and provided some of the data, as well as Liz Manzi and her team from CCRM Canada for their collaboration in generating the second part of the data. And thank you again. 감사합니다.